Hey guys, my name is Adrienne and welcome to Organic Chemistry 2, Part 5 of these recorded sessions. So today we'll be going over for most of y'all Chapter 17 and in general benzene and aromatic compounds, right? So again, we'll do our study review first and then our summary later. So if you want to skip to the summary first, compare your notes or see what you're missing or see how I did my notes, feel free to check that out and then come back. If you want to do the review, because I know most of y'all just need the review, in OChem 2, practice makes perfect, right? Or at least close to perfect. Feel free to come and do the questions with me, or you can do them yourself. Screenshot them, um, write them down, and then do them. And then if you don't understand anything, come back and see the explanation. And whatever works best for you. There's a lot of different ways you can take this video and kind of apply it to what works for you. So um, again, as long as you're doing the practices, you should be fine. They're very representative of the chapter of what we're covering, of even of your exams, because I'm pretty sure your professors have a test bank, things like that, and that these questions are pretty similar, very, very similar. And again, you can twist them, you can rearrange them, you can, kind of manipulate them to whatever you like, and still, you know, practice different formats of how to word the questions, how to answer the questions, how to kind of see it backwards, forwards, sideways, things like that. So a lot of different ways you can study these. But for video's sake, for, smooth setup, let's get started with the review. And hopefully you guys, you know, learn something from it and enjoy it. And if anything, you guys have the review, right? You guys have a good review. So let's start out with our first page. So as always, pause the video, you know, take a couple minutes, answer them, see what you gather. And again, these questions are chronological, so they should be right, you know, on point with your notes, or your chapter, your PowerPoint, your things like that. So you guys are back. One, I got D. So which of the following statements about benzene is true? So this is all about benzene. This is all about aromatics, right? This chapter. So D is not true undergoes substitution reactions because yeah, it's true because it undergoes substitution reactions and not addition, right? So it's not D because if it does undergo addition reactions, then we'll lose that aromaticity, right? It's going to lose one of those pi bonds, which is not good. So substitution retains ring, right? So that's why it prefers substitution over addition. Okay, so two, again, I feel like there's always questions at least about hybridization, right? And I'm pretty sure you're gonna get questions about what other popular ones are there, like spectroscopy, things like that. So I'm pretty sure there's actually one in here. So, those things kind of they're general information, right? So you can kind of take them into any chapter and still apply to whatever your topic is. So those things are kind of like very conceptual, very all around. You need to know them, right? It's okay, right? So two, you guys should have gotten this one, and this one's just an easy one, B, right? And how do we tell? Well, these bonds that they're getting pointed at are sp2, right? So nothing special, nothing tricky about this. Um, oh, I put it the wrong way. Let me erase that. So nothing tricky, you know. So just like that, right? This is an sp2, this is an sp2. That's all there is to it. There's nothing fancy or tricky thing, anything to it. It's literally just that. What's the IUPAC name? So again, this chapter we haven't named. I don't think we've named since last semester with OChem 1. So we haven't learned aromatics before or benzene, so this is kind of where it's coming from, right? We need to know how to name them, but it's super easy, much easier than actually the other the past ones we've done, like epoxides or something. These are more like straightforward because most of these you're gonna rely on common names, right? So for three, what's the common name that we can come up with? So this one, the common name you guys should have gotten is the obviously the carboxylic acid is the more prioritized one, right? So you guys should have gotten D. And the way you can kind of do this is, let's see. So you have this structure, right? ClNO2 HOOC. Because when we name, we know that um we name everything else, the same, like longest chain, lower numbers, lower substituent numbers, things like that. Where is it going from? But we know we use common names for benzene, and we can't use multiple common names in one molecule, right? So we use the most kind of, yeah, the most common, or in this case, there's only one common, so that's easy. So this is our common, right? So that's called what our benzoic acid, right? So now that's our parent, benzoic acid, and we just number these normally. So we numbered it this way because it's the way we get the lowest number substituent, right? So 3-chloro-4 nitrobenzoic acid, um, things like that. And also naming. I don't think I've mentioned this. Well, we didn't really do it in OChem 1, but with naming, you have all four choices, right? Try drawing all those four choices and see if you can come up with a different molecule, what they should look like, right? So things like that, get the question, kind of deconstruct it, right? Like those fancy dinners or meals, right, in restaurants, like deconstructed whatever. So deconstruct it, right, and make your own. Okay, so for four, kind of same thing. What's our what's it called? Common name, toluene, right? So let me draw that actually. First, you have CH3, Br, Cl. So it's toluene something, right? So I always box the common name or parent, and then everything else is kind of just named. So you guys should have gone for this one, B, right? 2 bromo. Again, we numbered from this way because it's the lower number over here, right? So bromotoluene. So naming is fun. Um, well, aside, unlike I guess the alkyl chains, things like that, this is more dependent on common names. So you're definitely going to need to know your common names, right? Toluenes, benzoic acids, anilines, what else? Phenols, styrene, things like that. So let's see. Let's see if the next page has more. Okay. So yeah, things like this. So, you know, take a couple minutes, pause the video, figure it out, and see what you guys get. So for five, you guys should have gone A, and this is nothing fancy, nothing crazy. This is literally just what are these common names? So one is styrene, two is aniline, three is anisole, right? That's all there's to it. And I guess to point out, something to point out with anisole, anisole is an ether, right? So you can see it like this, right? So don't be alarmed if you see this and be like, what is this? This is an anisole, right? So that's pretty much all there is to it. And obviously there's a couple more. We saw toluene, we saw benzoic acid. What we didn't see is styrene. Well, actually, no, the styrene's over here. We didn't see phenol, but phenol is just alcohol, right? So things like that. And now, like I said, with six, again with the NMR and HNMR, things like that. So spectroscopy, and this is you guys should, you know, I don't know how long it's been since you guys, yeah, a couple of chapters, but hopefully you guys will remember. We're given what the formula, IRs, HNMR, and we're even given like the splitting patterns, right? So for six, you guys should have gone D, and why D? Well, we for sure can eliminate which one? Two. Two can be eliminated because our formula, molecular formula, shows only two oxygens, but two has three oxygens. So this one is canceled, right? And now we're down to one, three, and four. So let's go with three first because that's the one that's next. Three actually has four H and M R, and we were only given what? Three. We're given a triplet, a quartet, and a singlet. So for three, let's see. Let me redraw it here real quick. We have an OH, HO, right? So we have symmetry, obviously, right? Straight down. So where's our different environments? Oh, and don't forget this. So we have one, two, three, four. Four different environments, right? And there's no H here because those are already there's no more bonds, right? It's already bonded to four. One, two, three, four, right there. And it's symmetrical, so this side is the same as with the one, or I can even do this, two, four, three, right? So these are all the same, so there's only four. So that's too many. We were only given three. So now we're down to one and four. So for one, we have three environments, so far so good, right? So what are those three environments exactly? So we have one, two, three, right? And this one, right? So nothing too nothing too over the top, right? Oh, actually, so where did I make a mistake? You guys try and figure it out. Right. So how many symmetry places is this? There's up here and then to this laterally, right? So there's actually only two environments, right? There's two environments. So one, two, one. So this one only has two environments and a mark, right? So that leaves us at four. So let's see. Now let's do four. Let me find a space here. And let's just double check if it's right. So again, they're symmetrical, right? So we have one, two, three, one, two, right? Those are the environments. And now it's saying we have a triplet, a quartet, and a singlet. So this one would be our what? Triplet. Our one would be a triplet. Our two would be our quartet, right? So far so good. Um, Now three is the singlet. Again, aromatics are singlets, are broad singlets, I should say. And this, the chemical shift of 6.8 ppm kind of supports that, right? That it's aromatics. Aromatics are always between 6 to 7 chemical shift. So that's that. Okay. So actually, there is three environments for one. Let me So this is one again, right? I'm gonna put one over here. One is, I think yeah, I drew it wrong. So sorry about that. So this should have been something like that, right? Because it's CH2O CH3. So there's CH2O CH3. Okay. So one, two, three, three environments, but it doesn't have the triplet, quartet, or singlet, right? So this one's a singlet. One and two are actually singlets, right? Well, actually, all of them are singlets, right? So these are all singlets, so that's why it didn't work. All singlets. So that was that was it. So that was the explanation there. So nothing too crazy, right? We remember spectroscopy, so that's good. Okay. Now for seven, which of the following is not true of the Huckel's criteria for aromaticity? So now we're done with benzenes, right? Now we're getting into real aromaticity. So for seven, you should have gotten D, right? The molecule must have 4n pi electrons. Well, that's 4n pi electrons is anti-aromatic, not aromatic, right? So, but aromaticity must be cyclic, planar, completely conjugated. But 4n plus 2 pi electrons equals aromatic. So, okay, and 8, now we're kind of getting to the fun stuff, aromatic. And honestly, for aromaticity, there's only so many aromatics that honestly, after this review, you guys won't have a problem with aromaticity. Because, and even in your chapters, in your books, in your PowerPoints, things like that, there's a list of what are what the common aromatics, and those are pretty much what you'll see most of the time. Um, actually, all the time, because those are the only aromatics there are. So it's not going to be too crazy. It's like the common names with naming the benzenes. As long as you know those, you're pretty much good. But you know, we'll explain it a little bit more, so don't worry. Okay. So 8, you guys should have gone C. Oh, I don't know why I circled it. C. Um, again, this is just naming, right? But again, these are the aromatic heterocycles. So C, pyridine is the first one, pyrrole, furan, right? So those are automatically aromatics, right? So if you see the next question and you see that, oh, there's a furan, that's definitely aromatic, then that's aromatic, right? So that's it. So let's go to the next page and see what else we got. So now it's gonna ask which are not aromatics. And so again, pause the video, give yourself a couple minutes, and get back with your answers. Okay. So again, 9, like I said, right? Like I said, one is literally furan, which we said is aromatic. So that one's already out of the question, right? So for 9, you guys should have gotten C, and actually 2 is what? A pyridine, right? And then 3 is, I don't know what that is. 4. So how did we figure out which one is not aromatic? Well, even if we didn't know this was furan, right? Or this one was um pyridine, right? Did they say pyridine? So how do we figure it out? So let me draw them. We know they have to be conjugated, fully conjugated. They have to be planar. They have to be cyclic, obviously, and they have to follow Huckel's rule. So most of the time, you'll be dealing with Huckel's rule because that's an easier kind of bet, right? So I'm actually going to change the color here so we can kind of see better. So Huckel's rule aromaticity equals 4n plus 2 pi electrons, right? So how many do we have here? So each double bond will have one, right? Or I guess two. Each double bond will have two. One, two, three, four. So where do we get that other two, right? Because 4n plus 2, we have 4 times 1, so we need a plus 2, right? Well, it's one of these, right? So, again, going back to, I think the last chapter and even, yeah, conjugation, the p orbitals, right? We know lone pairs, so they can be in pi orbitals too, right? So that's why they're there. We know they have single bonds, right? And it has two lone pairs. So those lone pairs, one of those lone pairs is in the p orbital. That's why they count it in Huckel's rule. They count it as pi electrons because they're in the p orbital. Still, just because they're in the p orbital doesn't mean you can't be a single bond or a pi bond, right? And over here, 1, 2, 3, 4, 5, 6, right? We're good there. 1, 2, 3, 4, 5, 6, 7, 8. So that's not Huckel's rule, right? 1, 2, 3, 4, 5, 6. So that's why it's C, because this is actually anti-aromatic, because it follows 4N, right? Okay, so now 10, you guys should get, what is it, which spelling is most acidic? So this one's a good question too, because we haven't dealt with acidity in a while, right? So for this one, you guys should have gone C. And why C? So you can't just take this as is. You have to convert them into a way where you can tell acidity. And we know acidity, you can use what? Their conjugates, right? Conjugates. So acidity conjugates. So conjugate bases in this case. Um, so to get conjugates, we just take away their hydrogens, right? So for this first one, you guys, what would the conjugate be, right? And then so on and so forth. So this one's always tricky to draw. I've been drawing this for so long, I forget. 1, 2, 3, 4, 5, 6. There, something like that. And then this one, I don't know why I put the long pairs, I'll do that here, but okay. And then this one, and for 4, we can toss it out because we know um, conjugation, the more stable, the more acidic. So obviously that's not going to be the more acidic because it's not even stable, or isn't the most stable in out of those, right? Because it's no conjugate. So, well, I guess I can draw this, and we can cross this out. Cross this out. Not acidic, not stable, right? So the thing to kind of keep in mind, this acidity and conjugate bases is more stable conjugate base equals um, more acidic. So which one of these is the most more stable conjugate base? So now we can kind of look for conjugation, right? So which one of these are aromatic, right? So in this case, we'll have 1, 2, 3, 4, 5, 6, right? So this is in Huckel's rule. I mean, so actually, let me change it to the color blue so we know we're talking about Huckel's rule. So this has 1, 2, 3, 4, 5, 6, right? It has 1, 2, 3, 4, 5, 6, 7, 8. So that's a no, right? 1, 2, 3, 4, 5, 6. So this is 6. So both of these are 6. Both of these follow Huckel's rule. But now, what is the difference between 1 and 3? Well, let me change the color here so you can see where I'm. So this one is not fully conjugated, right? Because look how the separation between these two are. So this is conjugated, but it's not fully conjugated. Not fully conjugated, right? So that's why um it's 3, because it's the most stable, it's the most conjugated, it's gonna have the more acidic proton, right? So there you go. That's kind of how you do that. And with acidity, also, you know, it's the most common kind of forget forgetting it conjugates. They're so easy to forget because like you never know when to apply it. But have if you're dealing with acids and bases, always have that in the back of your head. Conjugates, because that's part of acids and bases, right? They make conjugates. So think of conjugates. Don't forget about them, please. Okay. So now let's go to 10. Oh, 11. 11. You guys should have gotten which of following is aromatic. So again, we kind of just did that, right? Um, and a lot of these are also what's it called? Common aromatics. So you guys should have gotten D, 2 and 4. So those two are actually like common aromatics you should know. So that should be easy. So, but anyways, let's do our little Huckle rule, right? Okay, I drew that really bad, but let's see. Okay, that kind of looks better. Okay, so this one, and we kind of just did this one earlier as well. So you see how they kind of super repetitive, but it's like, you know, but we can do them. It's good that they're repetitive because you don't have to study as much, right? Okay, so again, let's go with blue for Huckle's rule, right? So this one has 1, 2, 3, 4. So it doesn't follow the Huckle's rule. 1, 2, 3, 4, 5, 6. So follows the Huckle's rule. 1, 2, 3, 4. No. 1, 2, 3, 4, 5, 6. 6. So there you go. Huckle's rule. So if and again, this is another way of kind of, twisting the question. So these are aromatic, right? These are aromatic. What about these two? They're anti, right? So that's kind of a good way to kind of twist that. Okay, let's go with 12. 12, you guys should have gotten. This one is also one of those things like hybridization, right? So we kind of already did one, but D, you see, indicate the bond here. So sp3 and sp2, we know sp3, obviously the oxygen one, right? And then sp2 is the one connected to the benzene. So nothing too crazy there. So we can move on. Okay, okay. Now, again, pause the video, collect your thoughts, write notes, you know. Okay, so for 13, you guys should have gone D, right? So this is just a simple naming one. And then now for 14 and 15, it's just, again, the common names. For aniline, You guys should have gone B, toluene. Toluene is probably the most common one. It's just a methyl group, right? So that one's D, right? And now 16. 16 is a good one because again, spectroscopy aromatics are kind of like one of those like special ones, right? For H and MR, you guys should have gone what? A, right? And we kind of saw that when we were practicing for spectroscopy, how what's it called? Oh, actually, spectroscopy. So why A? So let's do this. Sorry about that. So A is actually what? IR, right? B is actually for CMR, and C is nothing, right? D is for HNMR, right? So your answer should have been D. But again, other ways to kind of reword the question, right? Which of these appear in the IR spectrum? So, so things like that. So these are good questions. Again, nothing too crazy. And since it's just a new kind of like we haven't named it before, you will get a lot of naming, right? So which is good because it's always easy to name, and the rules are pretty much always the same, right? You just have to know those couple common ones. So okay, that was a fast one. And again, a lot of spec, right? Okay, and this one is another different way of asking questions about H&MR. So again, take a couple of seconds and collect your thoughts. Give me your answers. Try and do them, and let's see what you guys got. So 17, you guys should have gone C, and why C? So first, I would do is A, B, C, D. We have a phenol, right? So draw them out. Anisole, which is what? The ether, right? Bromoanisole. No, put the D over here. Bromotoluene. Right. So which one of these? The HNMR is showing us three environments. Which one of these has three environments? So now we're talking about environments. So this has one, two, three, four. Right. This one has one, two, three, four. So that one stands for. So both of these have four environments, right? So no. This one has one, two, three, right? Oh, and these are all aromatics. I forgot to put double bonds inside, but it doesn't matter, right? Well, actually, let me do them just so you know, we don't want to be inaccurate, right? Okay, so there we go. It says so. This has three environments, which is good. And let's see, one, two, three. So three environments as well. So now we're between C and D, right? So we should be able to get it down to C and D. Now, how do we narrow down even more? So, and I'm gonna do a different one, a different color. So this one, we have this one is a singlet, right? These are the two is the what? Doublet. And actually two and three are both doublets. So doublet as well. So that's what we have in the chart, right? We have a singlet, a doublet, a doublet. So far so good. This one, what do we have? We have here a singlet. And over here we have a doublet as well, right? So now what do we do, right? How do we differentiate these? So here you have to kind of now, again, kind of the same thing with the chart, right? The chart, I don't know if you guys remember from a couple, or I guess a couple chapters back, when we were looking at the chart questions, how you first you do the environment, the splitting, and now you do the chemical shift. So now our chemical shifts are 3.5, 6.8, 7. So you'll actually see that, and let me do this here, that ethers are around 3.5 shifts, chemical shifts. And that's how you would have figured out it was C, because this singlet would have been in the ones, right? Because it's a sp3 CH bond. So that would have been, um, what's it called? That would have been down in the ones. So for this one, it's close to this oxygen, so it's more de-shielded, right? And it just happens to land over here. And these two, these hydrogens inside the aromatics are the in the sevens, right? And then you guys might be asking, what are the three H's and two H's? Those are the ratios, and the ratios are how many hydrogens are in that environment. So this singlet has three hydrogens, right? And that's why it has three H's. And then these have two, these have two. Same thing over here. Three, two, two, right? So that's how you kind of deduce, right? Okay. 18, you guys should have gone B is not aromatic, right? And this one, we'll do this one because this one's interesting too, because we're seeing a different molecule for the first time with the S. So let's try and see how we can find that out. Ooh, I feel like my drawings are just getting worse and worse. Okay, this one's definitely all stuff. Actually, there, I saved it. Okay, why is it B? So Huckle's roll. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, the lone pairs, right? Don't forget about the lone pairs. 1, 2, 3, 4. That's an anti, I guess, right? Anti. 1, 2. So 2 is, what would 2 be actually? 2 would be um nothing, right? It could be aromatic, right? 4 times 0 plus 2. So that one's a good one. What about this one? 1, 2, 3, 4, and then again, there's a lone pairs over here because of the charge, right? So 6. So that's what we got with B. So all of these you can solve by puzzle. A lot of students try to figure out with like cyclic, planar, things like that. Planar is a little bit tricky because it just depends, but most of the time they should be all those things we're working with are planar, right? Unless specified not planar. So okay. 19, which song is aromatic. Again, you guys should have gone D, and why is that? So this one's actually a good one too because this has a different reason why we chose D. So let's do that real quick. Okay. So N, okay. And then the last one over here, and this one's actually a good one because we've never worked with kind of nitrogens. and you'll see nitrogens a lot in aromatics as well. So again, our Huckle's rule: one, two, three, four, five, six. That one's good. Um, one, two, three, four, five, six. That one's good. One, two, three, four, five, six, seven, eight. That one's not good, right? Let's see. One, two, three, four, five, six. That one's good. Now, let's see. Why is it not these two? These are aromatic as well. Well, again, there's a big gap right there, right? They're not fully conjugated. So, not fully conjugated, right? So, boom. Now we're down to the, well, actually this one. But you guys might be asking, why, and I'm going to do this pink. Why do we count these lone pairs and not these lone pairs? Now, we've been saying that lone pairs um, can be in p orbital, right? Lone pairs can be orbital. We know that. Lone pairs can be wherever they want. Well, in this case, these already have p orbitals because of that double bond, right? But in these cases, these don't have double bonds, so that means their lone pairs, one of their lone pairs, will be in the p orbital. Does that make sense? So think of it as if you have lone pairs and you don't have a double bond, one of them, one of the pairs is in the p orbital, right? So for example, we have another lone pair over here, right? But those aren't in the p orbital; they're in another orbital, right? And think of it as this: so n lone pair over here, another lone pair over here, right? Lone pair over here, lone pair, and obviously only the top, only one side is the p orbital, right? So let's choose the top part as the p orbital, p, right? Unlike this, this still has what? The one lone pair, right? But that one lone pair is not in the p orbital anymore because these and the double bond is the p orbital, right? The ones over here. So that's why we don't count the lone pairs if you already have a pi bond because obviously that pi bond is in the p orbital, right? Pi bonds equals p orbital already, right? So that's why. That's why I found that interesting because a lot of students forget that as well. And this also goes for other atoms, not just nitrogens or oxygens, right? As long as they have lone pairs, this goes. So that's what you have. So now let's go to the next and last question, 20. And this is super easy. Why is the following not aromatic? And you guys already see that big gap, right? 20, you guys should have gone deep, and that's all. We don't have to worry about, it's obviously cyclic. It has 4n pi electrons. It has 4n plus pi 2 electrons. But that's not the reason why it's not aromatic, right? So, well, actually, hold on. Yeah, it's not continuous. But why is it? It has 4n pi electrons and it has 4n plus 2 pi electrons. What does that mean? I guess we can do it. Okay, so let's see. How many pi electrons do we have? We have one, 2, 3, 4, 5, 6. So that follows the 4n plus 2 pi electrons, right? So it's not 4n. So yeah. Okay. So now that that's done, again, we'll move on to our summary, right? So let me close this out and let's move on to our summary. So first things first, obviously benzene. Benzene. So this is the structure. We know that, or we know it could be represented as that, right? It's just resonating. Simplest. And it has 4 degrees of unsaturation, right? Because it has 3 pi bonds and a cyclic, right? 3 pi bonds and 1 cyclic there, and does not undergo addition reactions, right? And we know that because if it does undergo addition reactions, it's gonna break the ring, right? So we don't want to break the ring. Um, does substitution retains ring, right? So that's what we want. So, and this is also called Kekule. I don't know if I'm saying that right, but it's a person's name. Kekule is pretty much why benzene looks the way it does. So it's pretty much how the structure is, right? Structure, planar, right? And it's all the same length. The all the bond lengths are the same. All CC bond are equal. Oh, are equal length, right? So that's just something to know about calculate. Um, so let's go to the next page, and so it's gonna be about benzene. So benzene. So this is where the kind of like the pi electrons come in and the conjugation, things like that. So we have, let me change the colors here. That's kind of what you guys have in your book, right? And then, okay, and then we go with red. Okay, and then, and you got to see how where the conjugation happens, because where the conjugation happens because they overlap, right? And obviously one of these is the pi orbital, right? And let's see, this one has the conjugation, right? Has those electrons in them because they just keep spinning. And these pi electrons, and you guys already know these, make benzene electron rich, right? And react with strong nucleophile. So obviously, right, electrophiles, nucleophiles, what have you, simple reaction, we know that. And now let's go into naming, right? And into naming, we know common names. So name substituents, then add benzene, right? So our common names, unless there's a common name, then we use the common names, right? Common names, we have toluene, phenol, aniline, aniline. Let's see, benzaldehyde, right, and styrene, styrene. So those are common names, and you use the common names when it's not when you have them, when they're available. Like we did with the questions, common names again. If you have substituents, you just name the substituents as is, then the common name. So instead of benzene, you can do the common name, right? So I'm gonna put that in quotes, right? Okay. And obviously, IPAC rules apply, right? Alphabetical, lower numbers, things like that. Okay. Now let's talk about benzene as a substituent. Mm, as a substituent. So that means, again, same thing with every ring, right? If the alkyl chain is longer, obviously we're going to use that instead of the ring. So let's say, right, let's say it's cut up there and then it's a bigger chain, blah, 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 and it's just a substituent. It's going to be called phenol, right? Or pH. Sometimes it's abbreviated as pH. And you kind of see that sometimes in reactions, pH, blah, 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 or something, right? Um, benzyl is already another one. Benzyl. This just has one more carbon. And arrow are just any aromatics that are substituents, right? Any arrow. So things like that, nothing too crazy. And then of course stability. Stability will, you know, more stable. Again, more stable equals lower heat of hydrogenation, right? So we know that. I think we've known that because again, heat of hydrogenation is kind of just like energy, right? The more stable you are, the less energy you have, right? Things like that, vice versa. Um, so true for all aromatics. So nothing too crazy, right? Okay. So now let's go into aromaticity. So we talked about benzene, now we talk about aromaticity. So again, it needs to be what? Cyclic, planar, complete conjugation, and for Huckel right? So cyclic, obviously, overlap, p orbitals overlap, adjacent, right? Planar, planar, so they can conjugate, delocalize, right? Completely conjugated, every atom. Huckel's rule. So now Huckel's rule for aromatics and anti-aromatic, or n plus 2 or n, right? Pi electrons, pi electrons. So we know that nothing too crazy. The only thing here is also there's a distinguish to distinguish aromatic, anti-aromatic, and non-aromatic equals missing more than one requirement, right? So if it doesn't follow Huxley's rule and it's not completely conjugated, then it's non-aromatic, right? So things like that. Yeah. So don't confuse anti and non-aromatic. I guess that's what I'm trying to say, because anti-aromatic is still all of these plus 4N, right? But non-aromatic is missing like planar or something, or Huckel's rule, or doesn't really follow. Non-aromatic doesn't follow any of these, right? So yeah, that's aromaticity for you. So now let's go into more aromatics, and in this one, um, we'll have the common aromatics. So first we'll have the fused rings, and these are aromatics. And I don't know if we saw some in the review, but pretty much same concept, right? So this is the naphthalene, naphthalene, and then okay, right, and this one's our anthracene, and I don't know if this one will fit, but let me see. Okay, oh, perfect. Okay, and yeah, these are all aromatics, right? You can move all of these double bonds completely around. And this one's phenanthine. Phenanthine. So we have fuse, and we have our heterocycles, and we saw this some of this in a review. And again, knowing these is pretty much like, automatically knowing the question, right? Because um, again, we saw a lot of pyridines, right? So if you know it's a pyridine, it's an aromatic. NH. This one is drawn weird, but this one's pyrrole, right? We saw that as well. Histamine we didn't see, but we saw furan, right? And after a while, you get used to these, and it's pretty much just automatic, you know. Okay, this one H2N, and you can even do the Huckle's rule and to double check, right? But yeah, this is the histamine. So after cycles, let's see the rule for this one. This is like the last one, and then we have the ionic compounds. So we have, and we saw this one for sure. So it kind of helps knowing, memorizing these, I guess, but you don't have to. It's an H right there, but and this one's the cyclopentadieno anion. Okay, now I have to see if I have room for this one. One, two, three, four, five, six, seven. Okay, that's a seven membered ring. Um, okay. This is a plus, right? We saw that. And this is called tropylium, tropylium cation, right? So these are all the aromatics that you should, you know, start thinking about. You'll see most common ones, especially these heterocycles and the ionic ones. These are you'll see these a lot, you know. So memorize them, because you saw the questions. A lot of them literally ask, "Oh, what's this structure? What's this structure?" So, what's this structure, right? What's the structure of naphthalene? What's the structure of anthracene? So, okay, last but not least, and this one is an interesting one. You may or may not cover it depending on who you're taking a class with, but molecular orbital theory. So this is the theory of how you kind of find aromaticity. So describes bonds as the math. So I probably lost a lot of you guys with math. Mathematical combination of atomic orbitals that form molecular orbitals. Okay. So where electrons are, where electrons are. So basically, number of atomic orbitals equals number of molecular orbitals, right? Yeah, yeah, right. So the way you can kind of uh, another way to tell instead of just Huckel's rule or things like that is this. You guys probably seen this already. Energy. Um, and we have here, our orbitals, right? And then let me do the colors again. Kind of the same thing we did with the um with this. Let's see. Okay, and then and I'll explain after I draw all these what I'm doing. So we have here kind of the orbitals, right? Obviously the orbitals, the jumping, the electrons and stuff like that. So these is your anti-bonding, and I want to leave room for some place. So this is your anti-bonding, right? And we talked about anti-bonding last time. It's pretty much just denoted by an asterisk, right? This is your bonding, um, bonding, and this is your non-bonding. So anti, non, and then bonding, right? So bonding, obviously you're bonding, so you're pi, so you have both electrons present, right? Non-bonding, you have one of each, so because they're not bonded, right? They're not fused. Anti-bonding, nothing is in them. Nothing is in them. So now we call this um, the destructive. I'm going to do a different color here. Destructive bonding, and then our constructive bonding, right? Destructive and constructive bonding. And this ties into the, and I'm going to write it here, in inscribed polygon method. So inscribed polygon method. And what that is that inscribed polygon method is pretty much follows the Huckle's rule, but in a more geometrical type way. So inscribed polygon method is you have a circle. Oh, that's a pretty good circle. And you cut it in half, right? And it's pretty much this. So you have your anti-bonding over here, anti-bonding. This is your non-bonding because it's in half, right? Non-bonding. And then all this second part is the bonding, right? So this here follows this, right? And up here we have the HOMO, the high orbital, right? And then the low, LUMO, HOMO, LUMO, high and low, right? Which is the destructive, constructive. So same thing over here. Anti-bonding has um, no no bonds, no electrons, no electrons. This one has one electron, right? Each, right? And this one's full. So filled, this is one each, one electron each, right? And the way you do this, again, in this circle, you draw draw molecule or draw aromatic, right? Draw cyclic with 1 point down, right? So let's see. Let's say a pen. Um, actually, yeah. Let's do a pen cyclo. Actually, no. Let's do a benzene. So you would have something like this, right? And then obviously your double bonds. And again, 1 point down, right? 1 point. So there, there, there. So now what do we do? Well, what we do is, how do we find out if it's aromatic or not aromatic, right? Well, the thing about this is it still follows Huckel's rule. So 4n plus 2 still follows Huckel's rule, so we don't have to we don't have to worry about that. So now what do we do? Well, as you can see here, each of these atoms, right, are in the field. So we have, and let me do blue. Actually, no, let me do green. So these are all the bonding, right? One over here, one over here, one over here. And those are all in our field section. So 1, 2, 1, 2, 1, 2. There's no atoms in our half point, right? So that's 0. And there's no bonds, or anti-bonding is 0 as well. So we have a total of what? 6 electrons that we're counting. And does 6 follow Huckel's rule? It does, right? 4n plus 2. 4 times 1 plus 2 is 6. So now we know benzene is aromatic because this is what you do. So that's kind of how you do that. It depends who you're. I don't know if this got confusing or not, but it really just depends on who your professor is if you go over this. But I think it's fun. Honestly, the hardest part is drawing the cyclic with 1 point down, because if it was like, well, I mean, a cyclic, um, yeah, actually, it shouldn't be that bad because even like a pentane, like a pentagon or whatever, you can just point it, the house going down, right? And if it's like a square, you can just do a diamond thing, and it's just gonna be two, right? So things like that, two in the bonding, and then nothing else. So that wouldn't be aromatic, right? So that's that. With that being said, hopefully that made sense. And yeah, hopefully you guys learned something. Hope you guys, hopefully you guys, enjoyed it. Hopefully it wasn't too confusing, But again, if you guys have any specific questions, or if something really didn't make sense, ask your professors, go to lectures, ask your Ask the I, right? They'll have the answers for you, and don't be scared to ask them questions. That's the whole point, right? To ask questions. That's why they're there. I mean, if there'd be no point if you can't ask questions, right? Because why not just read from the book and not have professors at all? You know what I mean? So ask them questions. They're there to help you. Ask your friends. I'm pretty sure they've taken OChem before. Um, but yeah, that's all I have. Until next time, hopefully you guys come back. I'll see you guys. Bye.